All right, well, good afternoon, everyone. Welcome to part two. It's my pleasure to introduce today and tomorrow's lecturer, Dr. Jacqueline Chen, who is a distinguished member of the technical staff at the Sandia National Laboratories in Livermore, California. What shall I say about Jackie? Jackie is probably the world's foremost expert on the use of direct numerical simulation for turbulent reacting flows. She really works at the frontier of not only combustion physics, but also at the frontier of computer science to do some of the largest calculations of any type of physics, never mind turbulent combustion. Jackie has numerous awards and distinctions, too numerous to list. Maybe one of the more recent distinctions is she was just inducted into the National Academy of Engineering, which is pretty much the highest honor someone in the U.S. can have. So it is certainly my pleasure, and I hope you will join me in welcoming Dr. Jackie Chen.
Now is it on? Nope, it is. Okay, can you hear me in the back? All right. Thank you, Michael, for the thoughtful introduction, and welcome everybody to this session today, this afternoon, and tomorrow afternoon on. I'd like to talk about DNS and computations of turbulent combustion and the convergence of computation with high-performance computing advances. And probably just for most of you, this will be less of a tutorial and more of a sampler of what's going on in trying to get CFD and reacting flow codes onto high-performance computing, supercomputers, and that evolution. And I'll probably show a number of examples of DNS, of turbulent combustion, as it relates to flame stabilization, auto-ignition, and various other processes that are relevant to designing fuel-efficient, clean-burning engines for transportation as well as for power generation. So let me turn on my laptop here. Okay, so the first part, there's 6 parts today and tomorrow, and the first lecture is going to be kind of a motivation and a little bit of the underlying numerical and mathematical description for the kinds of simulations, direct numerical simulation of turbulent combustion. And so as all of you know, combustion has been around for ages, right? Since the beginning of time when we relied on fire to provide heat and for cooking and for all kinds of things in daily life. And as technologies evolved over the centuries, steam locomotive and plants for making iron and steel all relied on heat and fire and combustion before we really had sophisticated technology. And then as we moved into the Industrial Revolution and cars and trucks and airplanes and all kinds of things that we are used to in our daily lives are ubiquitous around us. Kind of take them for granted, but there's still quite a lot of research and technology developments that need to happen to make combustion burn more efficiently and cleaner, generating less emissions of soot, particulates that we inhale, and greenhouse gases that are destroying our environment. And so there's a lot of work that can be done still as we move forward. Combustion's by no means near its end. I think we're still got another half a century at least of combustion, and certainly for large energy-intensive devices or high heating devices, they're going to rely on combustion for a long time. I know in the US, combustion accounts for well over 80% of the energy that's used, and of that, transportation is a significant fraction of that energy consumer. In fact, it accounts for almost 2/3 of the oil usage, and also unfortunately is a fairly substantial contributor to greenhouse emissions like CO2. In the past, there have been various government mandates, less so in this current administration, but there were a lot of government mandates to reduce petroleum use, cutting it by as much as 25%, and greenhouse gases. I think that there's still a mandate to do that throughout the world, especially in developing countries that are hungry for energy and also need to develop and adopt technologies that are more clean burning. So where is all that energy that we derive from fossil fuels and from renewables, solar and wind and other sources, and nuclear going? This is a chart that is put out by the International Energy Agency that looks at where sources and where that energy is going. And so you can see that a lot of the energy is transformed into fossil fuels, the coal, natural gas, petroleum, oil, and a large percentage of it goes out to industry and to transportation, and less so for electricity and heating of buildings. And then other little bit of natural gas, nuclear energy, and renewables on this bottom side goes to generating power and heat for industry and for heating our homes. And this is just another way to present that same kind of information, maybe in a graph form or a pie chart, however you want to ingest it. But you can see that industry accounts for 31%, almost balanced with transport for fuel consumption, and residential and other services account for the balance. And so as we go out in time, you can see that actually transportation has gone up since 1971. It's continued to grow, whereas some of the other sectors, residential and industry, are kind of flattening out. If we look at transportation itself, you can see where are the energy sources coming from. And you can see that in time, well, back in 2012, it was primarily coming from gasoline and from diesel fuels, with a little bit, and jet fuels for airplanes, and very little from natural gas and from other electricity sources. As time goes on now and into the future, you can see that natural gas is becoming an increasing percentage of the way that energy source for transportation. And electricity is still, while it's growing a little bit, it's still not a major contributor. So by and large, we're still going to rely heavily on diesel, gasoline, jet fuels for airplanes, and an increasing amount of natural gas for engines. Now, if you look at electricity generation sources, over time, again, this is starting from 2012 on to projecting out to the future, renewables have certainly increased and will continue to increase. And likewise, natural gas has become a more substantial, there's growth of that as a percentage of the total. With the tiny, petroleum's negligible in these bar charts. We also know that burning petroleum and some of these combustion fuels contributes to the anthropogenic generation of CO2, and that's causing the temperature to go up over time. And this is plotting the temperature anomaly over several decades. This chart's probably a little bit outdated, showing the surface mean temperature that has changed as depicted by the red line, and the black. The red line is the 5-year average, and the black line is the annual mean, with the error bars shown in green. And so the result of burning is that our temperature is rising. And the major source of where these greenhouse gases are coming from is primarily from burning petroleum and coal in probably equal amounts, roughly, and natural gas lagging a little bit behind. But these are the sources of where these gases are coming from. And so we've got to find a way to mitigate CO2 and greenhouse gas generation as we combust. I also just want to make the point, which you probably all know, that the energy density of various sources of fuel varies a lot. And in particular, this plot is showing different energy densities from gasoline, diesel fuels, natural gas, and electric sources way out here in the purple column, which is negligible. But you can see the energy density from petroleum fuels is so high, and that's why I think combustion is going to continue being the primary source for energy for the future, for a long time in the future. And so, for example, it would take about 1 gallon of gasoline is enough to charge up your iPhone for a day for almost 20 years, to give you a perspective rather than plugging it into an electrical outlet. So I think that everybody here can make a lot of contributions to building on the science foundation that we need in technology to understand the fundamentals for combustion, which is why you guys are all here, that's necessary to develop more predictive, more accurate models that are validated against experiment, against theory, and that are multi-scale, because a lot of the physics now happens at over a wide range of scales and is coupled across decades of scales. In order for these models to then be deployed to industry so that they can shorten their design cycle. For IC engines, this plot shows that it takes typically, 15 years to go through a full design cycle and get a new product out to market. And so it would be extremely advantageous for industry to shorten the product development cycle and the ability to move their new products out to market if they had a better scientific understanding with more predictive models in the end. And so if we just take IC engines, for example, we know that IC engines have lots of multi-physics in them. They're multi-scale, so it spans maybe 6 to 10 decades of scales, where in both spatial dimension as well as in the time dimension, where the typical engine cylinder bore diameter is 10 centimeters or so for an IC engine, much larger for a marine engine. And so if you take the largest scales or the cylinder geometry, so that would dictate your turbulence integral scales that might go from several millimeters to centimeters in the smallest device, an IC engine. It only gets larger when you move to gas turbines or to burners. And then chemistry, when we talk about flame scales, we're talking about millimeters or submillimeters, and when you get to fine resolution of the internal structure of flames or of ignition fronts, you're talking about microns. And as we move up in pressure, flames get thinner and ignition fronts get thinner, and so the spatial resolution gets even smaller. So in addition to the large range of scales, we also have to deal in combustion with chemical complexity. And there are the simplest fuel that we burn is hydrogen, which has 9 species, but if we move up the carbon number to more practical fuels, C8 and above, you can quickly encounter species numbers on the order of thousands of species and 10,000s or so of elementary reaction steps that describe that chemistry in a detailed model. And so, of course, using that kind of information in any kind of fluid dynamics CFD simulation is impossible. So there's intermediate steps where you have to reduce and make assumptions about that detailed model in order to get it into a CFD code where you can start to couple other multiphysics, including turbulence, with that. Oops. Did it come back? Press screen to return. Okay. And then beyond chemical complexity, we also have to deal with multiphysics. So we have turbulence, gas phase chemistry, but most hydrocarbon fuels start out in a liquid phase, and so you have to atomize and vaporize the fuel and mix it to form the proper mixture, proper ratio of fuel to air, and sometimes diluents like exhaust gases to form the right mixture that you want to combust. And so you have to deal with sprays, you have to deal with downstream of combustion, especially in fuel-rich mixtures, you have the formation of soot. So you have precursors from the gas phase chemistry that allow you to generate, to nucleate soot, and then you have chemistry that describes how you agglomerate or make those soot particles bigger. And then eventually that soot is oxidized. And so you want to understand that entire dynamic process of soot formation and its oxidation in the particulate phase, which is and all of these processes are tightly coupled in space and time. So this is a real grand challenge to solve and to study both experimentally as well as computationally. So at a most fundamental level, I'm going to focus today not on all of the multiphysics, but mainly on the gas phase interaction of turbulent entrainment mixing, and some of the chemical interactions that occur when you, in a flame, or when you're trying to ignite, self-ignite a mixture, for example, in your diesel engine, as you raise the pressure and temperature to the point that reactions start to occur. So at a fundamental level, turbulence has the role of entraining the ambient air, or air diluted with exhaust gas recirculation. It advects, strains, and wrinkles a flame, creating more surface area for burning. And so most practical devices are not laminar, where molecular diffusion and reaction couple, but you get greater efficiencies if you inject a jet at high velocity and create a turbulent environment that is much more efficient at combustion, at creating surface area. So that's the positive side. On the negative side, turbulence also creates the conditions for very, very high velocity gradients, or strain rates, that can remove mass and heat from very early or incipient kernels that are trying to accumulate radicals and heat. And so you have this balance between generation of mass and energy from chemical reactions. At the same time, you have transport that either brings necessary mass from reactants or from recirculation zones, but at the same time it removes it. So there's this very delicate dynamic balance between reaction and transport, both at the molecular as well as at the turbulent scale. We also know from our fluids courses that turbulence is not just, doesn't happen at one scale, one length scale, but it happens over a broad range or spectrum of scales, from the largest scales, as I said earlier, that are dictated by the geometry of your combustor, on down to the smallest scales, the so-called Kolmogorov scales, where the energy is dissipated into heat or by viscous forces. And so there's this turbulence cascade that eventually entrains mixes until you have molecular mixing, reaction occurring at the very fine scales, and it dissipates out. Now, chemical reactions typically occur at the small scales, at the fine dissipation part of the spectrum of turbulence. And so they're kind of, and they're interesting because many of the reactions that we care about generate heat or are exothermic. And so that in turn can affect the turbulence. So through heat release, through gas expansion and dilatation effects generated by these exothermic reactions at the fine scale, you can reduce the turbulence intensity locally, and also through density effects. And so you can modify perhaps the energy transfer, which is typically for non-reacting flows in the forward direction, going from large to small scales. But it's possible in the presence of flames or ignition or plasma sources that you might have reverse energy flow, or that energy can find itself in other portions of the spectrum and modify the turbulence. So turbulence and chemistry are two-way coupled, modifying density, modifying property changes like the viscosity or diffusivity. Oops. Why does this keep going off? I guess. Huh. Okay. I'm not sure why this is not showing up there. It shows up on my laptop. Hang on. Let me just. You guys have any questions yet? Try that? Okay. Oh, there it is. Yeah.
One of the things, just to clarify a little bit of what she said about turbulence, she told you trying to get faster mixing helps you with faster burning rates. She's told you something about if I get too high, I can have dilation of systems. And there are two things that can affect that are really important. One is I get faster burning rates, but I still have materials that haven't been burned out. And turbulence, mixing, and dilation have effects on how fast those emissions are destroyed. And additionally, and overall, out of all of this, when she talks about efficiency of engines, it's pretty low, right? Where is all of that energy going? It's being lost as heat to the walls of the chamber for integrity. And so that's affected by both the turbulence level near the wall, in terms of transport, and also the temperature. So this coupling of turbulence is ubiquitous in all of these energy conversion devices. And it's one of the hardest things to couple into systems accurately, including chemistry.
Right. And I would add that on top of the energy transfer to the walls, that you also have materials problems because it impacts the integrity of the material if you have really high point-wise heat loads or average heat loads that cycles through. Like for example, in a gas turbine, you want to make sure you keep cooling, film cooling or something near the wall to prevent those high heating rates. I just unplugged it and plugged it back in. It seems to work.
Okay, well, it was shaky. It wasn't connected.
Yeah, okay, I'm good for now. Thank you. Okay, so, and then one last point of turbulence is that a healthy amount of it is good, especially when the fuel and oxidant are not mixed but separated. But if you strain it or you put too much turbulence on it, you can actually, and the chemistry can't keep up, you can quench it. And so you have extinction either locally or globally. You can blow out a flame, and that would be really bad. For example, if you're in an airplane or high altitude, you want, and there's a whole bunch of issues that people are working on how to do relight at high altitudes if for example, flame goes out. Okay, and the simplest example of that is shown in these pictures where, we've all had birthday candles where if you blow a little bit, it seems to burn more intensely, and if you blow too hard, it goes out. And non-premixed flames are notorious for having extinction limits, where if you go beyond that, you're gonna put out the flame. Premixed flames often are more robust, especially when you have large recirculation zones of hot product gases surrounding these flames that always supply heat and temperature to the flame. And so most practical devices do have stabilization mechanisms like bluff bodies. Bluff bodies meaning like something like a I don't know, a flat shape behind which you have recirculation zones, or you might have a cavity or backwards facing step that also provides physical creation of recirculation of hot gases that can help to stabilize flames when the reactants, the fuel and oxidant, are mixed together. Okay, so another motivation for studying combustion here is because over the last decade or so, the fuels, the number of different kinds of fuels that we burn in engines is evolving rapidly. In addition to the more typical hydrocarbons that we burn, gasoline and diesel and aviation fuel, there's a move to burn even more heavy hydrocarbon fuels coming from oil sands, oil shale, coal, as well as all the renewable fuels that you read about in the news, like ethanol and biodiesel, biogas. Even now, people are looking at burning things like hydrogen and ammonia. And so a range of types of fuels is evolving, and as such, that has implications for the devices that they have to operate in, the engine technologies. And so for IC engines, there's a lot of activity going on in direct injection, directly injecting fuel at opportune times as the piston is moving up, where the pressure and temperature are optimal for generating a charge. And a lot of times people use split injections or multiple injections to modify that mixture formation. And I'll go into that more probably tomorrow morning. But there is this notion of creating the right reactivity levels in an engine, and you can do that through a number of means. One way is to mix fuel and oxidant or an additive. Another way is to modify the chemical properties of the fuel that you inject, something that has high cetane number that would be more reactive, more able to ignite sooner, versus something that has low cetane number like gasoline or isooctane that is more difficult to ignite, and or methane, that's probably the worst fuel on the planet to ignite, has very, compared to hydrogen, which is the simplest to ignite. So finding that right chemical mixture and then forming the right balances through entrainment mixing and heat transfers is important. As society is moving towards trying to lower emissions, we've been driven more towards burning fuel lean in premixed modes and actually in mixed modes of combustion. So I don't know if you all know, but you can burn non-premixed where fuel and oxidant are segregated. You can burn premixed where fuel and oxidizer are uniformly mixed upstream, or you can have some combination of the two where you have partial premixing. And you can also have a premixture that's generally we think of premixed combustion burning into an inert reactant stream, but you can also imagine that if you have hot products moving around and recirculating, or you have autoignition intermediates ahead of it, that you could actually be propagating a partially premixed flame into a soup of reactive intermediates, so igniting mixtures that are not inert. And so what we refer to these kind of mixed regimes as so-called mixed mode combustion, which is still very much poorly understood at this point. And certainly the models don't reflect this, these modes of combustion, which from a practical standpoint, you want to burn fuel lean, premixed, so you avoid high temperatures and the generation of nitric oxides. And you want to burn lean so that you don't generate soot and particulates that occur under richer mixture conditions. Okay, so just to give you an idea of the types of engines that are out there, we all many of us drive gasoline engines, and these traditionally are spark ignited. So you spark near top dead center, and it generates a small kernel, premixed kernel that propagates outward in the engine as it's mixed. And then the other idea is using compression ignition, where you compress up the gas mixture, and then you compress up, and then you inject through high pressure injection systems the fuel into a isentropically heated ambient, and sometimes you've got exhaust gas recirculation mixed in with the ambient, and then it auto ignites. Usually that ignition starts at relatively low temperatures. These are high pressure engines at 40 to 100 bar. And so as the temperatures come up from ambient to about 750, 800 Kelvin, you start to develop low temperature reactions or low temperature ignition. And those generate intermediates that then get bootstrapped into hot ignition, which occurs typically about 1100 Kelvin or above. 1200 Kelvin above, and eventually you form a flame, a diffusion flame around the whole thing that is lifted a little bit, stabilized off of the injector, and the point at which it stabilizes, which I'll discuss more tomorrow, this lifted stabilization is anchored, we think, by some kind of partially premixed propagation into a low temperature ignition soup. And then lastly, there's another concept called HCCI, homogeneous charge compression ignition, whereby you have temperatures are low enough, the mixture is dilute enough that you volumetrically auto-ignite as opposed to forming any sort of flame that you would in the other two forms. And the issue here is, do you actually, I mean, if you truly volumetrically ignited the whole thing, charge, you would have such a high pressure rise rate that your engine would ping and knock as you drive. So you want to avoid that. So the question is, the challenge has been how to decide when to start ignition relative to the piston motion isentropic compression process, and then the subsequent combustion rate after it ignites. So you want to control that by various means of creating thermal temperature pockets, hot pockets with cold pockets, or stratification, or with composition stratification, through different mixing processes in the chamber through tumble and swirling motions, or through multiple injections of fuels that have different reactivity properties. So in this last mode, there's been a bunch of variants of this. There's been premixed charge compression ignition. There's, spark-assisted compression ignition. There's all kinds of variants on this theme. So it's not truly homogeneous, but it is such that you have predominantly auto-ignition with some degree that you can vary of flame propagation. So it's a combination of this so-called mixed mode combustion that's happening in there. So to burn efficiently and clean and with low emissions, there's this interesting chart where we plot the local fuel-air equivalence ratio. Stoichiometric is given by this horizontal line here, where fuel rich is above equivalence ratio of 1 and greater, and fuel lean is less than unity. And if you plot islands of soot as well as nitric oxide in this chart, and I'm sorry, the abscissa here is the temperature. And so if we look at where spark-ignited engines typically operate at near stoichiometric conditions, that's fairly high temperatures of in excess of about 2,200 degrees Kelvin, and that generates sits in the NOx island. On the other hand, if you high temperature diesels in the past have sat both on the NOx island as well as the soot island by burning fuel rich and at high temperature. And the move in the last 10 to 15 years has been to burn with low temperature compression ignition with lots and lots of EGR dilution, and to avoid the soot island. And so the concepts that I discussed before, principally the HCCI is one of the ideas, and also direct injection under low temperature conditions are ideas that the engine community are researching to figure out how to burn efficiently, but also avoiding emissions. There ends up being, when you burn under HCCI, there ends up being lots of issues with variations in load. So if you're burning under low load, you have problems igniting certain fuels. You're burning high load, you want to avoid high cetane fuels that would go off and lead to engine knock. So regarding power generation, there's also a move towards more being able to have flexibility both in terms of fuel types as well as the varying load that is encountered, especially in the face of intermittent renewable energy demand, supply and demand. So in the heat of the day, renewable energy is all used, but you may be able to store excess renewable energy in the evenings or when you don't need it, and be able to convert that energy into carbon-free fuels that are hydrogen-rich, for example, through electrolysis processes with water. And so there's a move to start to mix fuels like hydrogen and syngas together with baseload fuels like natural gas. And there's also a move to start to include biogas fuels as well into the mix for power generation in order to reduce the amount of our carbon footprint and for carbon capture. The problem with burning with hydrogen-enriched combustion that's different than natural gas, though, is that is an issue of safety primarily, and also of because hydrogen is so reactive, has such broad flammability limits and such short ignition delay times. But because it has, much broader than natural gas, but because it is so reactive, it also has an advantage that it lets engine developers switch out fuels rapidly or to do different kinds of blending during fast startups and during times when the load is transitioning. Hydrogen also has a smaller calorific value, and so it needs much higher volumetric flow rates. And you've got to worry about things like flashback, where the flame will flash back from a combustor into the fuel injection or premixer section, which is a safety issue and can really damage gas turbine parts. And so there's a lot of fundamental challenges to lean premixed hydrogen-enriched combustion in gas turbines. Flashback being one near walls and also in the bulk fluid. You can have flashback. Another issue is with fuel injection and flame holding and stabilization. So how you inject hydrogen, whether it's through co-flowing or cross-flowing jets into the oncoming stream, is an issue because of the mobility of hydrogen to find its way back into a fuel injector. Hydrogen is also quite energetic, and so it generates very high heat release rates, and that can couple with the acoustics in your combustion chamber and generate unwanted thermoacoustics and noise that can amplify and damage your engine. So these are some of the challenges. Just to give you an idea, one concept that has become popular recently is looking at staged gas turbine combustion with reheat. This is a concept that was originally developed by ABB, gas turbine manufacturer, for high efficiency load flexibility and low emissions. And recently, I think GE and Alstom and now Ansaldo Energia, an Italian company, have taken over and improved this axially staged reheat combustion concept that's used in their very large gas turbines, the GT36, which I think generates something on the order of 300 megawatts of power. And the first stage in this combustion system is a premixed combustion stage that's stabilized based on vortical motion and premixed flame propagation, whereas the hot products, vitiated products of combustion that come out of the first stage enter a mixing tube where additional fuel is injected, fuels that could be more reactive than natural gas, like hydrogen or syngas, like I talked about. And then that second sequential combustion stage that's heated to temperatures well above 1100 Kelvin or so burns primarily through autoignition as opposed to flame propagation. And so trying to find the right balances of fuel injection and the right temperature, inlet temperature for the second stage is a challenge. So this is just a diagram showing this, this reheat combustor. We're adjusting, as I said, the firing temperature of the first stage lets us control the ignition delay time for the second stage in the sequential burner. And so you want to control the inlet temperature to the sequential burner and the flame position because that affects the ignition length or ignition delay time, since that second combustor burns mostly in an autoignition mode. The second inlet temperature needs to be decreased, as I said, to not have it ignite too early. But you don't want to decrease the second stage flame temperature and derate your engine. And what you can do is because it's got two stages, so you can adjust to the different load demands, you can derate the first stage by decreasing the temperature, and that can be compensated by shifting or injecting more fuel into the second stage. And therefore, you don't lose any of your power. So from this, I'd like to then transition to some of the research paradigms. In combustion, we typically work on experiments, theory, and computation. And in the last, 30 years or so, experiments in laboratory scale flames, both at ambient as well as at high pressure of flames, premixed, non-premixed, mixed mode combustion, as well as ignition, are providing a wealth of data, especially with the advanced laser diagnostics that are available today. So you can really measure in detail the temperature and the species composition, the concentrations, as well as the velocity field at various locations. So this provides a lot of data that we can use to understand and start to develop models with. Computations also play a very complementary role to experiments in that computations allow you to have precise control of the parameters. So you can actually explore different phenomena in isolation, which you may not be able to do in a physical experiment. You can also do computations at different levels with different degrees of detail. So you can resolve everything from the largest scales down to the smallest scales through a direct numerical simulation, or you can resolve partial information, or you can average all of it, right? So you can decide what level of detail is necessary depending on how you're going to use that data. Computations also have full specification of the boundary and initial conditions of all of the scalars and the velocity field, which is something that experiments often can't provide and is necessary in the development of models. It's also relatively less expensive and faster to turn around computations in a design cycle than it is through experimentation. Just as lasers have really taken off, and the development of lasers has taken off and applied to combustion, computational power through high-performance computing, as well as the development of numerical algorithms, has also advanced rapidly. And I think we're kind of at a time now where there's a wealth of data coming out from both computations as well as experiments. And there are lots of opportunities for data analysis, data analytics, various types of manifold reduction methods and regression methods that we hear about for machine learning, which can be applied to our field, turbulent combustion. And so it's an exciting time because there is all this data and there are these new tools for allowing us to understand our data better and to make predictive models from them. So I think I've described this, and I just want to say that, as I said earlier, combustion's multi-scale, it's multi-physics. The governing equations that represent combustion, I'm going to talk about in a moment, are large, high dimensions because we have lots and lots of species in addition to the mass, momentum, and energy that we transport. And computational costs very rapidly becomes prohibitive because of the large number of degree of freedom that we have to solve in a realistic system. So typically we might, on today's largest supercomputers, solve on the order of anywhere from 10 to about 100 transported species, so number of species here would be, let's say, 100, plus the 5 conserved variables. But because if we want to do a DNS, we have to resolve all of the range of scales from the largest to the smallest, and we have to do that in 3 dimensions. It quickly gets into tens of billions of degrees of freedom that you have to transport, and you need to carry that out typically for several milliseconds at least in order to see phenomena like combustion or like autoignition delays and things like that, and to get converged statistics. So it's still not a fast turnaround if you want to do highly resolved simulations with chemistry, even on today's largest computers. The spatial scales for turbulence, mixing, and flames are kind of summarized here. We know from Kolmogorov cascade theory that the smallest Kolmogorov scales, eta, are proportional to the ratio of the integral scale to the turbulent Reynolds number to the 3/4 power. We also know that in a computational domain size on the order of L, right here, that you need to discretize that domain to resolve the smallest scales, the Kolmogorov scales, at least in an incompressible flow with 1 or 2 grid points. And so the number of grid points is dictated by the length of your domain size divided by the mesh spacing. We also know that the number of mesh points then has to be greater than, in a single direction, has to be greater than in scales with the turbulent Reynolds numbers to the 3/4 power for the momentum field. And also for scalar fields, the Batchelor scales are the comparable analog of the Kolmogorov scales for momentum. And the Batchelor scales for gaseous fuels of interest, for example, hydrogen air, has got a Schmidt number, which is the ratio of kinematic viscosity to the mass diffusivity of about 0.2. And heptane air has a Schmidt number on the order of 2.4. Both of these are typically of the order, most of these are of the order of unity. And so hence the length scales required to resolve both the scalar fields as well as the turbulence fields are comparable. Chemical length scales that are needed for resolving turbulence are not typically fine enough to resolve the internal structure of flames or ignition. And that factor, the rule of thumb is it takes about 10 to 20 grid points across a flame thickness, its thermal thickness, to resolve the reaction layers inside of it, which we are looking to do. And so if you take that into account, then it's much more expensive. The number of mesh points required for a reacting flow is much more expensive than it is for a non-reacting flow. And so I've kind of summarized here the spatial resolution requirements are you need to resolve the Kolmogorov scale with 1 to 2 grid points. The number of mesh points scales as the range of scales that you're trying to resolve, from the largest to the smallest cube, because you're doing this in 3 dimensions, where and if you consider that the turbulence scales are proportional to Reynolds to the 3/4, and you do this in 3 directions, then you have the number of mesh points scales as Reynolds number to the 9/4, which is a pretty daunting scaling, considering that most practical Reynolds numbers are of the order of a few thousand. And so we can't quite get there. I think the largest Reynolds numbers that we can actually directly resolve are of the order of about 1,000 at this point. Oops. Okay, and kind of have said this already, that the range of scales is large. The number of species is also large, so we have large degree of freedom. Number of species of between 10 to 100. Comparably, we have very, very significant time resolution requirements dictated by the acoustic Courant-Friedrichs-Lewis CFL condition, where the time step has to be smaller than the grid mesh spacing, the ratio of the mesh spacing to the sound speed. And we also have to worry about things like the chemical time scale, which can be defined based on flame time scale, which is proportional to the ratio of the flame thickness delta compared to its propagation speed, the laminar propagation speed, SL. Another way to define the chemical scale is to look at the species mass creation rates, or perhaps to look at the maximum reaction rate time scale. And more formally or mathematically, you can look at the eigenvalues of the reaction rate Jacobian to determine those chemical time scales. So the limiting time scale is the smallest of the chemical, acoustic, and advective time scales that you have to march at if you want to resolve that phenomenon. Let's see, how are we doing for time? How about if we go for a little bit longer and then we take a break and then come back? Okay, how about 5 more minutes and then we'll take a break? So given this daunting range of scales that we have to resolve, it's impossible to go and resolve everything from the quantum scales that describe chemistry all the way up through the continuum scale. As I said at the beginning of the talk, that will span anything from 6 to 10 or more decades of scales. And since it's so multi-scale, and we're not dealing with molecular approaches in this talk, we're dealing with mostly continuum scales. We have this moving window right now with HPC where you can directly resolve about 4 to 5 decades of scales. But you can decide where you want to put your moving window in this range. Whoops. And so our focus here is to look at DNS and in the continuum scale and develop the parameterizations that would let us bootstrap information upscale into engineering calculations, both for large eddy simulation as well as for Reynolds averaged simulation. There's also a move recently to go more down to smaller scales in the mesoscale region, where we are using particle methods like kinetic Monte Carlo and coarse-grained molecular dynamics or lattice-Boltzmann methods to start to look at interactions between particles of more fundamental chemistry parameters and their interaction with a little bit of hydrodynamics, and doing that at a more fundamental level by solving the Boltzmann equation rather than the Navier-Stokes equation. It's an exciting area. I'm not going to have time or scope to discuss that right now, but I think a lot of the interesting physics and technologies that are moving more towards plasmas or other fast chemistry processes that are accompanied by fast hydrodynamics or transport processes allows for coupling between chemistry or temperature fluctuations that are out of equilibrium, that can't be described by equilibrium. These would be non-equilibrium effects, where both the chemistry and thermal fluctuations are thermalizing at a rate that is comparable with the mixing rates, for example, behind a shock wave or in a rotating detonation engine. or plasma. There are lots and lots of interesting topics there, and some of these atomistic simulation approaches are getting large enough, and especially on these large computers, that you can start to couple transport with chemistry in these non-thermalized regimes. And so from that, we hope to improve upon the Arrhenius rates that we all use in our mechanisms today, and maybe provide correction factors or even new parameterizations to describe some of these other regimes that are out of equilibrium. But anyway, I'm going to focus more on the DNS in the continuum regime for this talk. As I mentioned earlier, you can look at different types of approximations in the continuum regime. Anything from Reynolds average Navier-Stokes, where there's no attempt to look at resolving any of the scales, and so you average out in time and space all of the scales. And this is typically what industry currently uses, because they need to turn around a large number of parameter studies very quickly on a workstation or on a very small cluster. If you increase the complexity, you can go to a large eddy simulation, which resolves, for example, in this energy spectrum, the resolved large scales on down into somewhere in the inertial range or even into the dissipation range on your mesh. And then you have to model the physics that's beneath your grid, so-called subgrid physics. And this would include models for the scalar fluxes, for all the scalar fluxes, as well as for the unclosed subgrid reaction models. DNS, then, on the other hand, is where all of the turbulence scales are fully resolved. There's no closure model for the turbulence, per se, but you still have constitutive models for molecular transport and for chemical mechanisms that are included in the DNS for a reacting flow. And this is the most expensive but most accurate method of all of them. And so you can see from this sequence of images on the bottom what a DNS of the heat release in a turbulent Bunsen flame looks like. And when you filter the DNS equations, you end up with the large eddy simulation showing the resolved scale LES, and you'd have to model the information that's on the unresolved scale underneath of it. And then if you average that, this is what the corresponding RANS picture looks like. So you can see a lot of the detail from the DNS is lost when you get down to a RANS level. Okay, so I think we should take a break so everybody can walk and take a 5-minute break and come back.